Good morning, I think, still. Can you hear me from the back? Okay, very good. So it's a pleasure to be at EPFL. Irvine is beautiful, I know, but Lausanne is more beautiful, I don't know. I have to choose between these two places, but both are nice. And today I'll be talking about, I think the morning session was beautifully about architecture. You learned a lot from there. But I'll be trying to build the entire system now and show you some of the methodologies that can work to build such AGI devices, systems. And feel free to ask me questions, stop me. It needs to be interactive, and I will probably also try to write in my slide some of the things. So it's more like a lecture. Although the type of papers and work that I put together, some is my work, some are from work from others. So you'll see that, try to get the message that I will try to put together. Just like other talks, I need to start, but I think by the time today, you already know why AGI is important. There have been already multiple talks trying to motivate you about the AGI. So I don't think I have any new information here, just, it's really the truth. It is going to happen, and I don't think we need to motivate ourselves anymore. A lot more applications. It's a very much application-driven. Commercially, a lot more companies. I remember this few years ago, this was just 50 billion, and it just got updated to 75 billion. So I think it is going to be 100 billion very soon, the prediction from Cisco and other companies that, number of IoT devices that will be proliferating. Am I right? So, and as I work in cyber physical systems, in fact, just to give you in fact, you saw my affiliation. I'm really a computer engineer, but I'm with mechanical engineering and computer science. So I had been working first, and since when I was in Europe for the first 10 years, from 2002 to 2010, I spent on silicon, embedded systems, low power design, architecture, and so, and then moved to understand cyber physical systems from a very high level, application driven stuff, and how it works, and how the optimization can be done from physics and cyber part. So I'm not going there. Today's talk is not about that, but feel free to come to me. How do I see this momentum going on? So just one application, autonomous vehicle, will be probably producing 40 terabyte of data, from its sensor in every hour. Am I right? So huge amount of data. So this amount of data, when I say that, many people, if you go to a different community, will be quickly ask you the question that why do you need AGI? Because we have huge cloud computing. We had been building over the last 40, 50 years, huge computing infrastructure from mainframes, different generations. Now we are in cloud computing, am I right? So theoretically, the entire computation should be done and can be done in cloud. So, and we have seen it is growing. It is not that it is not growing, it is growing. The truth is that today, the Google Drive, even a simple application, if you see, has 1 billion users already, by 2018, and another one is another storage is the 2015 Dropbox has already 700 million users. So there are a lot more users group into cloud. We all use, am I right? I'm sure all of you here have some interaction with the cloud. But the amount of data by 2025 is going to be 10 to the power 23, and we all are here electrical or computer engineers. We can imagine that 23 zeros. It is a huge number. So fundamentally, this entire thing is also an interesting thing that that now computing is a big, massive structure, physical structure. Like this is one of the largest cloud computing center. If you see in Citadel in US in Nevada, this is almost like 1.3 million square feet. So and I'm sure Europe has similar structure also in place. But the problem with this paradigm that our previous speaker was also trying to motivate you, and already you should know, that not all applications are equal. That means just you cannot put everything to the cloud, and some applications have different types of requirements. And how do we know that? Because as an embedded systems engineer for the last 40, 50 years, we had been designing systems. We know the specification like low power, low energy, real-time systems, reliability, so many other things, parameters that, not only functional, non-functional requirements, sometimes we call it. Am I right? We had been thinking about that, how do we tackle this thing? And that's exactly, people like us had been motivated towards this research that, how do we do embedded systems build up? So one of the application definitely is quite cool these days is autonomous vehicle, am I right? And autonomous vehicle, automotive by itself in Europe is an issue. Am I right? It is like the pioneering research happening in Europe, to be honest, compared to US. Because I have seen both sides of the Atlantic. And if you think from an automotive point of view, the amount of good type of research that happens in US, we talk about real-time system, timeliness, correctness, and all these things. And it comes with a huge burden of safety, because otherwise you will not be able to put your car in the road. It is impossible to get certification. So this has to be basically very, very carefully added. And one of the, just mathematically, if you think about that, the simple sensors, if you consider the 30 hertz sampling rate sensors, if you want to integrate in your autonomous vehicle, which comes with nowadays 10, 15, 20 sensors on board, and this is exactly 33 millisecond execution window, am I right? So now if you want to use the cloud, just one slide before, the one that I showed you, cannot tolerate basically this amount of delay, am I right? This is not possible. This is a huge amount of delay we are talking about. Second motivating factor, definitely, this is one side. The other application that is growing, as I said, wearables, a lot of wearables. We are talking about a lot of wearable healthcare applications. I know at EPFL, there is a huge group, David's group, basically doing an amazing work. At ETH Zurich, they are doing amazing work on wearable systems. And these wearable systems, if you look into this thing, the fundamental aspect that they need to do work on is the memory in kilobytes and megabytes. And it's a very small form factor that we are talking about, and they run on a very small, computing resources, megahertz level resources that these days. And also communication point of view, if you think, the last point, that this does not come with 5G or Wi-Fi, not very sophisticated. It comes with low power communication protocol. So all these factors add up that you cannot really run these applications into cloud, and it is not possible, and it's not the right thing. The third thing that a previous speaker, David, was also trying to, and everybody knows about it, about security and privacy. How do I trust my data? Because I cannot even, like 23andMe type of companies taking my genetic data and then getting merged with a big company, and then I don't know what's going to happen with my data. Probably I have already signed that you can use it for some medical research, but later, that I probably didn't mean that, or I even did not read that. So security and privacy is a big issue, and it is already well known. People are very concerned about it. I am personally concerned. As I said, 2010 till 2000, and still now I'm doing another part of my research, big research, is CPS security. Data, CPS, sensors, are all the security, and this is not the talk I'm going to talk here. But this is another paradigm. Machine learning security, yesterday, our first speaker from Meta was talking about it. So it falls into that dynamics here. So these are the three reasons you can take today that we need to do edge computing, but there are many other reasons we can probably come up with. So what is the alternative? So do the computation and the storage as close as where the data is. So, and that's what we call edge computing, am I right? And this edge computing architecture, if you look into from a point of view, farthest is the cloud. We can talk about edge or fog nodes, sometimes we call, and there can be even further. So you can create hierarchy of fog, close by servers. There are, different literature have different architecture, but it creates a hierarchy of computation. You can think about, how do we create different hierarchy. And the possibility is that this type of architecture can alleviate the communication delays that we try to say there is a problem. And it is definitely can play with the power numbers, energy numbers, help you to play with an optimized, and definitely can help probably some security stuff, am I right? And now the question comes today, what is the power limit for a embedded systems engineer like us? What is a low power? What is the definition of low power? Am I right? And we have pretty much very, very low power MCUs, and we have the GPUs coming from NVIDIA, putting into car. So edge computing, this definition needs to be clear, and these requirements typically come from the device specification and application requirements, because the same embedded systems or edge AI can have a very different wide spectrum of power budget requirements. So for example here, if you see, I try to draw this diagram. So if you see from the very left edge, you have small microcontrollers. Probably even you can use the RISC-V architecture based on RISC-V or PULP architecture. You can build a very low power devices. And then if you keep on going at the right end, these are typically from NVIDIA coming high performance edge AI, edge computing devices. So it is typically, we can call this a TinyML. I think the TinyML community is trying to push this word. And if you go to the right side of this graph, it's more like a still age, but has really quite good computing power. So you can clearly see that, we are not constrained to only MCUs or, small ARM-based microcontrollers, but we can really vary our computation, and many more hardware architecture, FPGAs, and other things can also play a role in this, diagram. So this is from the definition point of view. Now if you see from a application point of view also, there are different requirements or challenges coming. Like for example, if you are following the autonomous vehicle AVs and NVIDIA's synchrony, how AV is developing with the application and what is NVIDIA coming up with, you will quickly follow that NVIDIA PX2, which we used to in our lab, had like 12 tops, am I right, at 25 watt. And this was in the early 2010, 12, around that time, 14, even for quite some time, still in use. And then NVIDIA came up with AGX, am I right? And that is like 320 tops, lot more operation. But see the power number, 500 watt. We're talking about AGI 500 watt. And then now if you follow now, you can order basically AGX, which is 800 watt. And probably you will not get because of supply chain. There is a big problem. We ordered one, we still did not get it. And if these requirements are increasing. Although you can claim that the tops per watt is increased, of course it is getting better and better, but but at the same time TDP, baseline TDP is basically increasing. So why it is concerning? Of course the TDP, you need to understand that TDP is concerning because in automotive typically we never cared, because you will see in a second that I worked for battery management for like 5-6 years, BMS system design. It was not even my concern that computation, I should think about the computation power overhead. And it was for autonomous electric vehicle, it was all about actuation power optimization. But now, today, it is even with the basically with the AGX and this type of AGX Orin architecture, the amount of battery power that you use while driving is almost close to 12%. So you see that a car is really using a lot of battery power, and in electric autonomous vehicle, this battery comes basically reduce your driving range. So these are now any more siloed problem. It is not any more siloed problem. If you go to an automotive company, you have to think from a holistic perspective that how much I can drive. As an user, you just care about that. How long will I be able to drive safely, of course, and you want everything else. But this becomes really a problem. And the other problem, that Promise came up with from application side challenges, that okay, fine, we have been really talking about vehicular communication, V2X communication mostly, with the hope that it will alleviate a lot of communication delays, it will allow more perception, better perception, it will allow more intelligence. That is true, that all these things are true and a good promise. But if you now start looking into this thing, from an engineering point of view, that although everything looks good, DSRC, 5G, whatever you call that communication protocol you are taking here, it comes with always a connectivity problem. There is a lot more uncertainty playing here, and also a lot more application you cannot do. It has a limitation on number of applications that you can probably run on these devices. So, for example, one thing here, if you just take a 720 pixel camera and at a megabit of 20 megabit per second upload, basically, it requires 1.1 seconds to upload your data. So these are really, and we're talking about 8 to 20 sensors already today. So, and also multiple AVs can basically contain and compete for the same bandwidth, am I right? It's 5G or DSRC, because in the car there are a lot more dynamism happening that needs to be shared. So these are the really application driven problem. I'm trying to convey the message today. Even other requirements that is coming from the application, for example, the second application that I mentioned about already, mobile health. In the mobile health application, interestingly, it is not like a car, that you build a car, all cars can be same, all are safe, looks good, low power, XYZ, human are not same. My physiological parameter and your physiological parameter, although we come up with the wearable devices that I'm building, may not be basically reacting in the same way. So it needs to be customized for each person, okay? So it is quite an interesting problem. And the second thing within this very tiny ML paradigm is that we always talk about, doesn't matter, we have to harvest energy. So there are a lot of research happening, there might now also some product available where you can harvest energy from different sources, am I right? So, and harvesting and this relying on intermittent sources can be a real problem in real deployment and real world. So these are the system state, these are the problems that you need to be aware of from a very engineering point of view. So what do we do? So the point I'm trying to make here, after all this slide, the point is that you cannot look building a system siloed. You cannot, as I said, if you are looking into system only from hardware side, the message that I'm telling, if you are not looking into requirement side, if you are not looking into scenario side, if you are not trying to understand a real deployment, the system, your part may look good, but as a deployed system or an overall system, you will fail in several cases. And that's how many product or many system eventually fail. And that's the thing eventually I learned from cyber physical systems design, that we look into our problem, but cross-layer problems or cross-domain problems typically we avoid. So just try to do this cartoonish diagram that what should we be careful about. So in the edge device, if I create the hierarchy and abstraction layers, definitely the bottom is the most exciting. We are all excited about the hardware part. We need a lot more research, and it's in the early stage of hardware design, and a lot more fantastic stuff happening. All happening into CPU design, as David was mentioning, GPU side, ASICs, a lot of interesting ASICs coming. I have a lot of friends who are excited about hardware accelerators, approximations. A lot of work are happening in neuromorphic computing in the last 10 plus years. So a lot of things. If you go to the design automation conferences, if you go to architecture conferences, you will see that it is exciting research time happening. On the algorithm side, like yesterday's talk, you have seen the speakers. There is, machine learning conferences are like the hot cakes these days. Am I right? So many, everybody wants to publish something. A lot more interesting applications are coming, algorithms are coming, like quantization, pruning, and dynamic models, and all these things are happening. The other thing is in application side. Now, in the other part of the world, people are from academics, from industry, from startups, Google, Meta, whatever you call them, they're all excited to bring their product into the market. So there is this hierarchy, just a very coarse-grained hierarchy I try to put here. And you will see that you want to put your task, data semantics, context awareness, all these things are interesting things are happening over there. And while you are trying to map problems from one layer to another problem, you need to be this graph might look misleading, because you probably want to also draw a diagram here while you are mapping, as I said, and you will see that you need to basically understand the cross-layer semantic, cross-layer relations between these different layers that people are working on. And then you can build your optimized architecture in that case, am I right? So how does it work, or what do you probably want to do? Probably what you want to do at design time, if I split the entire design process, at design time, you want to optimize your framework, and you want to try to see that you meet your specification, given a specification, and requirements, and interlayer dependencies. That I was trying to argue, that there is interlayer dependencies, lot of interlayer dependencies, that every decision you take, you can probably have an optimization criteria in the lower level if you want to do that. So you want to have to do that, all these things in the design time. Once you are done, looks good. At runtime, probably, I'm not saying use the word probably, because it is not always done. If you can do a design very constrained system, later in the example you will see, probably you don't have a runtime decision making anymore. But if you can allow a runtime controller to take decision, you probably can adapt the system based on the modus operandi. Am I right? Different scenario changing and conditions are changing. You probably can adapt this thing. So this is like the recipe. I would say this is how you design system at scale probably can follow. Now from a greater perspective, even if I raise my abstraction a little bit higher, that okay, this was good for one device. you have solved problem for my one device problem, but I'm talking about heterogeneous world, IoT, Internet of Connected Things, lot more device, they are all communicating, all are based on these things, and how does it look like? And am I right? So these problems can have a bunch of research challenges that can come today, am I right? With far-reaching application potential and challenges like system-wide optimization. Can I optimize considering multiple IoTs? Can I build collaborative intelligence? Am I right? That's probably the ultimate goal we want to do. We don't want dumb devices, only smart by itself. We as a human know, no matter how smart I am, I cannot solve a large problem. Only way we can solve problems if we in this room, all the students, if given a problem, we'll probably be able to solve larger problem. And this thing has been motivated engineers for centuries, that if this is true, that as a group of people, as a collaboration, we can solve harder problems. We have to bring collaboration among systems, devices, machines. And this is a different dynamics, different discussion. I'm not going to talk today, but I'm quite passionate about that, intelligence and collaboration. But distributed computing research, communication protocols, network topology, task scheduling, federated learning comes here, like the talk, fairness, personalization. So the point here is that as a student in the summer school, you go back with the message that, wow, you are doing amazing stuff. Whatever you're doing, you are entering or you are already into a research problem as a student that will keep you motivating, keep you really, help you to explore doing things for the next 10, 20 years to solve harder problems. Because when I was a grad student, I was not faced by this challenge, I can tell you. This is something, when I became a professor, this problem came to me. But I wish that, or maybe we solved other problems, at that time it was necessary, but this is a problem that's quite interesting for your generation of grad students to go with and try to solve this thing. So, as I said, that for a quite good number of time, 10 years, 5-10 years time, I've been trying to solve and learn about solving multi-objective optimization at a very high level, and that's why these are the couple of works just for the slide. I hope I will be able to share this slide later. You will see that we had been trying to use different dynamics and how to optimize electric vehicle, battery optimization, lifetime optimization, driving range, and all these beautiful parameters. As a computer engineer, it was quite interesting for me because I had to learn the chemistry, battery chemistry. I had to learn the mechanics of the car. And when I considered these things different way, the algorithm that I was able to build, considering interlayer dependencies, are much more robust and better. And that's those couple of papers that you see from my group got published in DAG, DATE, ICCAD, and several places with and they were highly appreciated papers. Received the best paper awards and so and so. So this is relevant because this knowledge, if I take now into my consideration, and if I try to convince you, then you will see that today. The type of challenges that we are trying to solve has multiple objectives. But in a simple words today, if you see that this is the machine learning hardware architecture, and this is typically we take a model, and if we take this model now, consider the hardware efficiency and accuracy, energy consumption and all, the classic way of doing it that you try to take a generalized model and try to optimize it for your architecture, am I right? And that's the back and forth design process that you are trying to do it. David was talking about quantization is one way, because embedded systems cannot host basically this large type of network, and we can achieve really, we can try to quantize as much as possible, and like both in the computation and tensor storage with a lower bit width, like integer 8, he was showing integer 4, and a different to achieve energy efficiency. And this has been, quantization has been a very successful thing to apply in this case. So in this quantization, one of the things is the binary neural network that you see, that in a binary neural network, the conventional way that you store the results immediately after the convolution layer. This is the convolution layer, and you store the results here after the convolution layer. So this has been done in the last I would say 7-8 years ago, or it was quite well known. But the thing that we moved from here, that we said, okay, even further quantization, or can we change the architecture? We came with EBNN type of architecture, and in EBNN type of architecture, if you see, the pooling layer is directly applied after the convolution layer, am I right? So here, the pooling layer is applied directly after the convolution layer, and you don't need to store that thing. So you don't need to store basically anymore the data immediately after the convolution. So it is a big gain type of thing. So this is one strategy that became very, very common in embedded systems engineers to use, or scientists to apply this type of thing. So along this line, one application, for example, most of the talks that I'll be talking, either I'll be moving from autonomous vehicle example and mobile health applications. So, stay with me. So you'll see that I'll go back and forth these two applications in both in the very tiny ML side and quite high performance edge AI side. So for example, this example that I took, trying to myocardial infarction, which is a common application that is a single lead myocardial infarction. And if you put into basically ARM-based Cortex M3 MCUs, then which has very constrained memory and computational power, you will see that you can probably apply this type of EBNN type of architecture, quite fit into this memory requirements and the type of memory overhead you have. So we have done this type of work, and not only us, many people are trying to do that, to be honest. So the research is quite in this domain in the last 5-6 years, I would say. And people are also researchers also try to apply network architecture search. Am I right? So many of you are here already familiar with network architecture search. In my group also, we had been from the early stage, we had been trying to see that how network architecture search can eventually improve this architecture design. So there are many people work, and you can use even real device to hardware in the loop simulation in the network architecture search to tune and for the next iteration, so that you can update the search space with real numbers. And with this type of mechanisms, you can eventually converge to a very small, tiny, and with your requirements that you are looking for. And it definitely, we have seen that it is much better to use the NAS compared to handcrafted model, am I right? Handcrafted design. NAS eventually converged to a much better architecture which has a better energy efficiency in this case. And this was quite meaningful. So now if you think from this example, what we learned a few years ago, or what we can generalize this thing, that most of this research around this tiny ML falls into this loop. So what is the loop? You take an architecture, you try to optimize the architecture, for example, like quantization, you deploy the basically network, come up with a deployable network, you put into hardware, get the evaluation numbers, again try to evaluate and try to basically solve the problem. So this loop eventually gives you a nice understanding of embedded systems design. And is it common? Yes, it is. And in this part, you can use tools like you can use the NAS, or you can use hardware software co-design tools. Many hardware software co-design tools like RISC-V, where you can have even some software and you can have your custom hardware, or in FPGA. So if now think that this is architecture that is the current trend, and all these companies that deploying machine learning at the edge are typically using this type of design process. So this is the you can say that this is the state of the art design process that we need to understand, and we need to mostly platform-based, single platform-based design under certain specific conditions and settings you are trying to optimize. So the reason I talked about if you see dynamic architecture in my previous slide, I was a little bit that if it happens, because still we are not using any runtime decision. Because at design time, you can already try to optimize for a particular application, particular scenario for a particular hardware. So this loop eventually gives you the optimal architecture, and you deploy it and you try to keep on running it. That's the state of the art eventually. So from this architecture is basically my research has been motivated that what are the things can we basically bring dynamic architecture even at the edge. Even if I want to, maybe I will sacrifice the memory, maybe I will need more computation, but the possibility of having a dynamic architecture at the edge is quite exciting as a researcher. And what are the techniques we can bring and how we can deploy this type of thing. So the point of bringing dynamic architecture is not that only I am trying to do. There is a huge, this slide you will see, there is a huge amount of interest from the embedded systems community eventually that about deployable, about machine learning and trying to bring dynamism there. And if you see the simple data flow on the top, you will see that you can do the optimization in a different layer. You can do the optimization at the simple wise, you can do at the spatial wise or at the temporal wise, am I right? So you can change this thing, and there are multiple ways that you can apply here. So for example, in the dynamic architecture, if you think about you can change the dynamic depth, dynamic width, and dynamic routing, and many other techniques, am I right? So into the spatial domain. In spatial domain optimization, you can do this optimization. If you see the loop, I was talking about optimization. And there are already huge design space, huge amount of possibility that you can apply there. Same thing also into the spatial domain, am I right? You can do at the pixel level optimization, for example, image, if it's the image. You can do at the region level optimization. You can do basically resolution level optimization. So different levels of optimization you can do also into the spatial domain. And also in the temporal, am I right? Like video and text. If you consider this type of data, temporal data, then you have different optimization possibility also into this data. And you can apply both this type of, to build your dynamic architecture, both during training and for inference stages, am I right? So clearly the possibility is huge, and designing the dynamic architecture, am I right? And again, if I want to go back to the original thing that I was trying to do, that at design time, I want to build a dynamic architecture. At the same time, I want to build a controller, simple thing. Build a dynamic architecture, build a controller at runtime. The job of the controller needs to be very smart, but as small as possible to select between multiple dynamic architecture. But also I have to make sure my dynamic architecture is small enough to fit into my network, to my device. So, you see the if I want to simplify my objectives, then these are the objectives that I'm trying to achieve to gain this dynamic architecture. So, among all these possibilities that you see here, I am not going to talk or walk you through all these things. I'm going to pick some of these things that are quite more popular, are getting quite, some of the ideas has been already gaining interest or has been applied in a very quite a lot into the community, and some of the techniques that I'll show are basically getting momentum here. So the one technique that many of you probably are already using, building that if you are into this research, is early exit. The question is, why do I compute everything, all the layers? Am I right? This has been if you are probably you don't if you know embedded system designer, we always try to compute as less as possible, but we try to get the same accuracy. This has been the driving force basically in embedded system, because if I can reduce the computation but gain my objectives, why not? Every transistor flipping will cost me dynamic power. So why should I do that? So these are the ideas that early exit, is it possible to gain or do early exit, has been motivating for the researchers all the time. So for example, here in this example, we consider the human activity recognition. You want to understand the human activity. And any question, by the way, so far I can take if there is any question from the audience. Okay, not. Let's go then. So human activity recognition and using it as an early exit example. So typically what happens, this you use your early signal processing stages or pipeline stages, then you come to a controller. So this is the controller here typically, and this controller decides whether you want to do the rest of the computation in the pipeline, in machine learning pipeline, or it is possible just to get an early exit and eventually do the classification or activity. So you want to avoid this computation, am I right? These two boxes you want to avoid. So these are this is the really way that the early exit algorithms works, or this type of architecture works. So for example here, typically as I said, most of this architecture typically until 2006, the state of the art that you use the confidence metric to build the control. And based on the confidence metric that you can build, and you can eventually take take which load you will take. But in this particular example, we did not use the confidence metric as a controller. This work, it got published recently, in fact, in IEEE journal. And we try to show that it is better to take statistical features from activities, from the collected sensor data, and if you use the statistical features, the controller is not misleading and eventually the performance may not degrade. And you see the amount of this computation and runtime controller is still much more smaller, and the overhead can be basically compensated by the advantages in terms of energy consumption that we are getting here. So as I was saying, that there was a paper in 2017, in fact, if you see this paper later, if you go back and read, they showed that confidence metric is not the right way of designing controller. You better, because there is a correlation problem, and you need to avoid. So this paper was quite a good paper, and 2016 paper showed the problem. This date paper showed the problem, and then this 2017 paper came up with some solutions that how to avoid this type of early exit controller design based on this. So the point, rather than concentrating on how with a single paper, I can tell you there are many publications along this line, you rather try to get the idea that you need to build a controller and you need to have a confidence on the controller, and the controller has to be better, and you have to make sure that F1 numbers basically, or the accuracy numbers does not degrade, or rather increase eventually by using the adaptive architecture compared to the baseline. So this is what you have to make sure that you can achieve using your controller. So with that, there are definitely, the idea was to get a huge energy optimization, and definitely we received basically a huge amount of energy optimization by using this type of adaptive architecture. And like any other numbers, I don't think this is exciting, this is just a paper, but you can think about that the idea was achieved, that we had been trying to use adaptive architecture, get some overhead. We had some overhead, it's not, but with the overhead we were able to compensate or get a lot more energy optimization. So this work had been quite a motivating thing in early exit type of work. Then we tried to ask, from activity recognition, we started looking into other mobile health application. One of the application is ECG signal, am I right? So this is a very important, like myocardial infarction I presented already. So that example has further motivated, we started looking into the signals itself. And we found that the signals, ECG signals, has a pattern by itself, and you don't need to use the statistical method, because the previous example in the activity recognition, the controller was based on statistical features, but statistical features also takes a lot of energy. By designing your statistical based on statistical feature, we found that it takes a lot of energy. Rather, we try to create something called template matching, and this paper will be presented at UBCOM this year. Still not presented. So in the template matching, that you can create some template from the data, basically from the ECG signal, and based on this template you can decide which architecture you want to choose, or whether you want to do an early exit, and this controller now can decide, can either continue doing it based on the threshold value, or it can eventually execute this layer. And also we have tested that whether the second level, so it was not a single level controller, it was a 2-layer controller. In the first level we try to see whether it basically goes over the coefficient controller, and then we have seen the confidence metric. If both these things matches, then we can say that this is a myocardial infarction or not. So the classification can be given. So this type of architecture further improves basically your energy optimization, but again at a cost. But compared to the statistical method I showed before, this is much better. And we try to use the statistical method also in this example, but the problem is that if the application itself can get some features that can be applied to use template is much better. That's the lessons learned. We found that we can use. But now you see the two methods to build a controller. And in both methods, we had been relying on application itself. So the point is, if you now go back to my hierarchy, that layers I had been talking about, abstraction layer, that designing the algorithm, I need to be aware about the application requirements. And at the same time, I need to be aware about the platform that I'm building. So it's a mapping problem, that one-to-one, and how you cross layer, and you cannot just design your algorithm and be happy with the F1 numbers and all these things. Oh my goodness, this is much better. No, you cannot. It has to be basically this embedded, and the relation has to be quite intertwined, and see whether it is really a deployable system. So you need to look into the problem from a very holistic point of view. So with that, I think These are good numbers, and we have tested all these things. I will definitely, I put all the references of the papers below. So as I said, I will be distributing the slide to the organizers, and you can get these slides hopefully. So now, the same process now, if I ask myself that, now I am quite confident that I can build an adaptive architecture with early exit. Looks good so far. Now, if I use, can I automate the entire process? Can I automate build the entire process? And this was, I think several people are trying to build a network architecture search again. Like the network architecture search I have shown for a fixed platform, like a loop, visual loop that is going, that you are trying to optimize. But now the adaptive architecture, you need that build architecture, at the same time you need to have the controller. So the question is it possible to build a network architecture search along that line? And a lot of research happening, and it can be multi-objective optimization. I want to optimize for accuracy, energy consumptions, and other parameters that you want to bring. And is it possible to do that, including the early exit? So in this work, basically what we try to do, this was ISLPD work last year. We try to use a network architecture, so try to get an adaptive system with early exit in it. And we use the confidence metric because this is the most state-of-the-art work, not our statistical method or the template-based one. But if I can do it for confidence, I can do it for other too. So that was the more generalization way. So don't get confused. And we used eventually this this 2017 paper I was mentioning came up with a called temperature scaling, and you can use this scaling factor temperature T to eventually solve the problem that we had eventually before in terms of calibration. So the calibration problem can be solved, and we showed that this is possible to build adaptive architecture with its controller in eventually network architecture search. And that is a interesting perspective, because it eventually again can optimize the further the energy into the design phase. Because we had been trying to build handcrafted, and we demonstrated that adaptive architecture can already reduce a lot of energy. Now, including the NAS, I can now find the optimal architecture at design time and design the controller, and eventually together I can come up with a dynamic architecture with early exit. Okay, so this is number one. So early exit, dynamic architecture with early exit. So the message you see, the way I'm going with a fixed architecture that I've shown, single platform, now dynamic architecture with early exit. The second one, I'll talk about three different possibilities. As I said, I showed you the big tree. Out of that big tree, I'm going to demonstrate three time. I think probably will need a long time otherwise. So the second problem that I'm still very, very interested about data fusion, because I believe that in machine learning, the type of thing we are going forward, one of the challenges, which was already a big problem for many, many years, data fusion, but it is going to be revised and relooked from a different perspective rather. And even it's more interesting if you think about heterogeneous data fusion, because most of the examples I was talking about are time series data. I didn't create any slides, so you have to understand that the heterogeneous data fusion way, you don't necessarily all the data have to be time series data. You can have basically a graph, some sort of text data, or voice data, or any other data, textual data, image data, together with time series data. How do we fuse this type of data, and can we put those models? Can we create models and put into embedded systems architecture? And can I use those architecture for perception? This is another area. It is definitely not probably well looked at, but as a student, as a graduate student and interested in this type of research, you should probably start looking at in these dimensions and this research area. But today, I'm already going to talk about some of the things that already complex enough, very, very complex enough, and how do we solve this thing using dynamic architecture. So in dynamic architecture, as I was talking about, sensing modalities can be affected, differently by various runtime conditions. Am I right? For example, this motivational case study, if you take about, again, like we try to do the stress detection with wrist-worn physiological sensors, and there are many, many sensors. Like, you have the accelerometer, you have the volume pulse, blood volume pulse sensor, electrodermal activity measurement sensors, you have the skin temperature sensor. And these sensors behave very differently, if you have any scenario change of scenarios, like if you have a motion, for example. You see that temperature sensor doesn't change any value. But the other sensor, like the accelerometer, basically starts showing some different value that should not be. So based on, you probably can think about that I have now many sensors, and using some part of the subset of the sensors, I probably can solve the same problem. Why do I need all the sensors? This has been a problem that, even in security community, people are trying to work on, that the same sensors that you are trying to attack can be also used for defend. It's like policing, social policing, many of you probably know. So similar idea, that I have a lot of sensors already built. I probably don't need all the sensors for a particular application. And I can infer the same instance with a subset of the sensors, or the same sensor. So the question is, which subset is the best, given the situation? Do I need all? So this is eventually the hypothesis that we try to work on. And using this, when we started working on, or in the literature, there are typically two ways that people do that. One is called the early fusion. In the early fusion technique, you basically get data from all the different sensing modalities or sensors, and you try to fuse them as early as possible into this early fusion module, and then you continue the other pipeline stages in machine learning. The second technique that people are trying to do, just continue all the early stage, keep on doing for each modality, and then try to basically, as late as possible, try to fuse the data. And then go to the classification type of decision. So these are the typically two trends, and both of them comes with their own cons, eventually limitations. So if you see the early fusion, it is quite susceptible to noise and sensor failure. And sensor failure is probably one of the most common things, and also the sensor noise. So both are really common. So so early fusion, you will see later that it's quite good. It's quite good in terms of energy consumption. But considering this problem, you will see that they are probably not the right thing to do that. On the other side, late fusion, you can already understand that all the intermediate features that we are talking about, you are not considering at all. You are absolutely avoiding any intermediate features. You are going to at the end and trying to fuse the data, and this is a problem. So this challenge that, how we can come up with, a sensor fusion technique into this AGI machine learning devices, that is energy demanding, and that is basically can be highly efficient to energy. So with that, we started basically this research area called hybrid sensor fusion. And in hybrid sensor fusion, the first example that I am going to show is from healthcare application. Later I will be talking about AV application in a second. In this example, the idea was that, from the sensory data that I am talking about, is it possible to, let's try to do some pre-processing in this data, and from this pre-processed data, try to train or get the context. Is it possible to get some context identification in the stage 2? In the stage 3, then basically I can create branches. And if you see in the branches, each of this branch is a different subset of sensing capabilities. Or there can be multiple branch for basically your input data that can be selected and be chosen. So, you start getting about, pick and choose type of thing, and multiple options in the branch classified. But one of the things you have to always remember, you don't want to really have a lot of branches, am I right? Because you have to store them. So it's a storage problem, and it's in embedded devices. So you want to optimize the number of branches that you are producing into this layer, and once you have the branches, then you can do the post basically late fusion. In this example, we have used a simple Kalman filter.